Hi everyone, I'm Sohail Khosravi and I'm a postdoctoral fellow at Technical University of Denmark. Today I'm going to talk about the modeling and simulation of heat exchangers in Aspen HYSYS. We will start with an example. As you can see here, we have a hot stream and a cold stream. And our goal is heat up cold water. Our heat source is CO2, which is captured from a CO2 capture process or any other applications. And the CO2 is available at 900 degrees C and 400 kilopascals. We want to produce superheated water at 450 degrees C and 100 kilopascals. Our cold stream is water entering at 25 degrees C with a mass flow rate of 20 kilogram per second, and our hot stream mass flow rate is 100 kilogram per second. To reach our target of 450 degrees of water, we need to use three different heat exchangers: an economizer, an evaporator, and a superheater. The water enters at ambient temperature and pressure, so it first passes through the economizer to be preheated. Then enters to the evaporator to be vaporized. And finally goes to the superheater here to become superheated steam. All cold side are water and the hot sides are CO2. To design this heat exchanger network, we will analyze the outlet temperature of the hot streams, which is CO2, and also we will analyze the temperature of the hot and cold streams in each stage and how the system is configured. Then we will simulate the system at Aspen HYSYS. So let's start with the simulation of this heat exchangers in Aspen HYSYS. Okay, as you can see here we have the environment of the Aspen HYSYS. First of all, we need to define our components in the system. We had two components, CO2 and water, so we need to define them. We can use the HYSYS properties or Aspen properties. I use the Aspen properties, which has the wide range of the materials. So then we need to search our component. We have a CO2. As you can see, the software found the carbon dioxide, and then we have water, and then we have our two components in our system. Now we need to define the fluid packages, because if we don't define the fluid packages, software will not recognize that what which equation of the state should be used for the simulation of our system. So we need to define the fluid packages. Okay, we can come here and say that, okay, we want to have ideal gas for the CO2, and then we can also define another packages for our water. One of the accurate equation of the states for the water and the steam is the steam MBS. We can choose it for the water. So we need to remember that the package 1 is ideal gas, which is related to the CO2, and the second one is steam MBS, which is related to the water. And now, after finalizing this step, we can go ahead with the simulation. We need to press simulation button here, and then we will be transferred to the simulation environment. It takes a little bit time, and so we need to wait for the software. Okay, now we are in the simulation environment, and this is the panel that we can find the different components here for design and simulate the energy system. We can drag and drop it here, and now as we defined our example as a heat exchangers network, we need to drag and drop heat exchanger from the panel in the right side. Okay, we had 3 different heat exchangers, so we need 3 heat exchangers here. And we can adjust them one by one, or we can move them as a group. Okay, we want to start with Economizer. We click on this exchanger. We can rename it to the Economizer. If you remember, in our example, cold stream was water, so we can come to the tube side of that exchanger and define that we have cold water as a inlet of the tube side and hot water as a outlet of the cold side in the economizer. And also we define the package 2 as a steam MBS for the water. So we need to select package 2 here. And for the shell side, which is the hot stream, we can say that we have CO2 here. But the number of the stream should be CO2 3 as we had in our system. And the outlet should be CO2 4. This is because of the order of the streams. For the cold streams enters to the economizer in the first heat exchanger for our cold stream is economizer, but for the hot stream the final stage is the economizer, so that's why we have the CO2 3 and CO2 4 here. Okay, now as you can see we have here our economizer with the hot streams and cold streams. Okay, we said that this is the cold water and this is the whole hot water and this is the CO2 3 and CO2 4. But at this point, software doesn't recognize that this is the this is the water and this is CO2. We need to define them. We can click on the one of the streams and come to the composition. If we come to the composition, we come here, edit, and define that the 100% of the this stream is water. So we say that 1 out of 1 mole fraction is water. And now the software recognizes that this stream is water. Then we can come here and we can define the inlet condition for the water in the economizer. We know that the temperature is 25 degrees C and the pressure is 100 kilopascals and the mass flow rate is 20 kilograms per second. So we can change the unit here as kg per second. Okay. Now we are done with the cold stream in the inlet of the economizer. As we can come to the properties, we can see the different properties of this stream. Molar density, mass entropy, mass enthalpy, mass exergy, and different properties that if we need to do any other and extra simulation or analysis, we can find them here. Okay, Now we want to define the outlet condition of the economizer for the cold stream, for the water. We say that we don't have pressure drop, and we say that it's 100 kilopascals. And for defining the temperature, to ensure that the outlet of the economizer is still in the liquid phase, we need to define a temperature for this stream 4 or 5 degrees C less than the saturated temperature. So we can say that this is 94 degrees C. As you can see here, the vapor phase fraction is 0. So we have still liquid in the economizer. Now we are done with the water and we can come to the CO2. Again, here we can click on the CO2 and go to the composition and define that this stream is CO2. Now this is CO2 and we can come and define the stream condition. We know the pressure is 400 kilopascals for hot stream and the mass flow rate is 100 kg per second. But we don't know the temperature of this stream because the hot stream CO2 enters to the superheater first. So then we need to simulate evaporator and economizer and superheater and integrate all these three heat exchangers, and then the software will calculate and find the temperature at this point. And also for this point, for the outlet of the economizer, we can say that the pressure is the same, we don't have pressure drop, and the mass flow rate is the same, but we don't know again temperature. Okay, now we can come to evaporator. We can rename it to the evaporator. Okay, in the cold side, in the tube side, we know that inlet is hot water and the outlet should be evaporated water. And in the shell side, we can say that CO2 who is inlet and CO2 3, which is available here, is outlet of the shell side. Okay, then as you can see, we have evaporator here also, and we need to define some parameter for our evaporator streams as well. Okay, let me adjust these streams. Our configuration looks a little bit better. Okay, so we have the evaporated water here. We can come and define the condition for this one. The pressure is 100 kilopascals and we don't know the temperature. We can say that the water should leave the evaporator as a saturated vapor. So we can say that vapor phase fraction should be 1, and then software automatically calculates the temperature of the saturated water at this pressure. It's 99.63. Okay, as you can see in the evaporator also we are done with the cold side and we need to come to the hot side. We did CO2 3 in the last step and now we need to do for the CO2 2. We know only the pressure is 400 and the mass flow rate is here. So we need to come to the superheater as a second one, as a third one. Okay, click on that, rename it as a superheater. Okay, in the cold side, the inlet should be evaporated water and the outlet should be superheated water. And in the hot side or shell side, inlet should be CO2 1 and outlet should be CO2 2. Now, as you can see, if we adjust this, we will have superheater also. Okay, we can come here to the superheated water and set our target. We said that we want to have 450 degrees C superheated water at 100 kilopascals. Okay, now we are done with the cold side, cold stream side, and now we can come here to the hot stream at the first point, and we can say that the pressure is 400 kilopascal, and as we had in our example, the temperature is 900 degrees C. As you can see, now if we define this, all the parameters should be solved, and now we have our completed heat exchanger network. And now we can say that we had 900 degrees C CO2 at 400 kilopascals, and also we had a cold stream at ambient pressure and temperature, and we produced 20 kilograms of superheated water at 450 degrees C and 100 kilopascal with using these three heat exchangers and utilizing the hot CO2 as a hot stream. And the outlet temperature as an outlet stream, the temperature of the outlet stream of the economizer is about 350 degrees C, which means that CO2 enters to our network, heat exchanger network, at 900 degrees C and leaves our network at 350 degrees C. And also the cold stream enters at 25 and enters at 450 degrees C. So this is a steam generator design and simulation in Aspen HYSYS, and now we designed economizer, evaporator, and superheater, and all three can be called as a steam generator. As a final step of our simulation, I want to show you something about the economizer's design. If we click economizer or evaporator or superheater designs, in general, the heat exchanger design. If we click in one of these heat exchangers and come to the performance, we can see some information here. Heat duty, heat loss, UA, which means heat transfer coefficient times area of the heat exchangers, which is calculated here. LMTD, logarithmic mean temperature difference. Hot pinch temperature, cold pinch temperature, and any other information if we need for our analysis. So also it's available for the other ones, for the superheater, and also for the economizer. And another thing is that we can have some plot for our heat exchanger here. For example, we can have temperature and heat flow plot for our heat exchanger. As you can see here, the y-axis is temperature and the x-axis is heat flow. And we have, for the economizer, we have hot stream as a CO2 and the cold stream as a water, and we have this plot. We can change the plot type for whatever we want, for example UA and other different parameters. Okay, I hope it would be useful for you. It was a brief introduction how we can simulate and modeling the heat exchanger networks in Aspen HYSYS.